Section 11.4, Boyles Law. The pressure of a gas depends partly on the volume of the gas. We talked about this a little bit. We'll just go over it again. If we keep the temperature and the amount of gas constant, then the pressure and the volume will change. If the pressures change, the volume will change. So if the pressure increases, then the volume decreases, and vice versa. And we talked about the hand pump, the bicycle pump. When you raise the handle up, it increases the volume in here, which causes the pressure to go down. And that draws air in through this one-way valve. When you press the handle down, now you're decreasing the volume, which increases the pressure, and that air gets pushed out through a different one-way valve and into whatever you're pumping up. So there are gas laws, and we talked about laws and theories, and a law just states what happens, and theories talk about why those things happen. So these are gas laws. They don't explain, they just describe. So Robert Boyle, back in the 1600s, discovered this relationship between volume and pressure. And again, it assumes constant temperature and constant amount of gas. And his law states that the volume of a gas and its pressure are inversely proportional to each other. And so down here in this equation, volume, this alpha symbol means proportional to. So the volume is proportional to 1 over the pressure. If the pressure gets bigger, then 1 over the pressure, that quantity gets smaller, and the volume gets smaller. If the pressure gets smaller, 1 over the pressure is a larger number, and the volume gets larger. These are, this illustration here is similar to some of the experiments that he did. He's got a glass tube. It's called a J tube because it's shaped like a J. It's closed at this end, and so there's a gas sample in here, and then there's some mercury in the tube. And the mercury will, of course, want to go to the bottom, but it will also reveal the differences in pressure between the inside and the outside. Because in here we have the pressure of the gas pushing down, and here we have the pressure of the atmosphere pushing down. And so we can measure the difference in pressure by the difference in the heights of the columns of mercury. So again, that unit of millimeters of mercury kind of makes sense. If we add more mercury to the tube, it's going to push more over here because now we've got the weight of the mercury pressing down, and it's going to squeeze this gas into a smaller volume. That gas can't get out. The same amount of gas is here as was over here. It's just compressed and squished together. But now we see that the difference in the columns of mercury is greater, and that tells us that the pressure is larger. So larger pressure, smaller volume. Smaller pressure, larger volume. And here's a graph. If you graph volume against pressure, as you increase the pressure, the volume goes down. And this is not a linear relationship, but if you graph volume versus 1 over pressure, then you get a nice straight line. Kinetic molecular theory explains what's happening. Boyle's law says this happens. Kinetic molecular theory explains what's going on here. So here we have 2 containers with movable tops, and this has a brass weight on it, and this has a larger brass weight on it. So that presses down on the top of this container. Excuse me. Here the volume is 1 liter. So we have a 1 liter gas sample, and we've got a few particles in there. Over here we have the same number of gas particles. The difference, though, is because of this weight pushing down, the volume is now half of what it was before. And then we have a little pressure gauge over here. At 1 liter, the pressure was 1 atmosphere. At half a liter, the pressure is 2 atmospheres. So we could look at that mathematically, because Boyle's law said that the volume was proportional to 1 over the pressure. So there we had 1 liter was proportional to 1 over 1 atmosphere, and 0.5 liters is proportional to 1 over 2 atmospheres. Because what is 1 over 2? It's 0.5, isn't it? This example was set up so that they were equal, but that's not always the case. But you see the volume went up, the pressure goes down. Any questions? So I skipped the explanation. What's going on here? Well, where does the pressure come from? The pressure comes from these particles hitting the walls. Pressure is the force with which they hit divided by the area. Well, here the surface area of the container is smaller. If these guys, they have the same mass, they're moving at the same speed because they have the same temperature. But now, because this surface area is smaller, they're going to be hitting the sides more frequently, and so that ends up being more pressure. Does that make sense? With the same number of particles, but now you've got more collisions because they're more confined together. So here's how we express Boyle's law. P1V1 equals P2V2. There's going to be several different gas laws, and at the end I'm going to show you how you can actually figure them all out from just one. And this is a typical gas law problem, and it's important to always read through it first. A cylinder equipped with a movable piston has an applied pressure of 3.0 atmospheres and a volume of 5.0 liters. What is the pressure of the cylinder if the volume is decreased to 2.0 liters? There's a lot of words in there, and there's some numbers too. And many students have trouble, taking the sentences and putting them into here. And so the best thing to do is to make a table. You read through it, you're like, okay, this is a gas law problem, let's make a table. And a lot of these are going to have 2 sets of conditions, and so I'm going to make a table here, and I'm going to have condition 1 and condition 2. And I'm going to find the first number that I come across is 3.0 atmospheres. Write the unit in your table. And atmospheres is a unit of pressure. So I'm going to title that column pressure. And I'm going to say, okay, that's the pressure in the first condition. And it says 3.0 atmospheres and a volume of 5.0 liters. Those 2 numbers go together. So they're going to go on the same line. So 5.0 liters. That's the volume. So I've got a volume and a pressure. Those 2 things went together. And then it says, what is the pressure? That's our question. What is the pressure if the volume is decreased to 2.0 liters? So the volume is going to be decreased to 2.0 liters. And we have 1 empty square in our table, and we should have 1 empty square. The question is, what's the pressure? And this is the pressure that's missing that we're trying to find. That's in the pressure column, and it's in the second row, so we're going to call that P2, and that's what we're going to solve our equation for. Any questions about putting the numbers into a table? We'll do a lot of this. Right now we only have 1 equation that we've talked about, so that's easy. We don't have to choose our equations. So we've got P1 V1 equals P2 V2. So we write that down, and then we're like, okay, look at the table. What are we looking for? We're looking for P2. So I'm going to make that red. So that's what I'm trying to find. I need to rearrange this equation. The equation is set up in a very general way. It's not solved for any one particular variable. And so I need to do a little bit of algebra and rearrange this. And if you have troubles with rearranging equations and my explanations in lecture aren't enough, please ask me for some help. Okay, I can explain it some other ways that might make more sense to you, or go to the math center and get some help. But you can't get through this chapter without being able to rearrange these equations. So we need P2 by itself. We want the V2 to go away. Well, if we divide this side by V2, V2 over V2 is 1. Anything divided by itself is 1. But we need this equality to stay equal. It's like a balanced teeter-totter. And if you put a 10-pound rock on one side and you don't do anything to the other side, the teeter-totter's not going to be balanced anymore. You have to put a 10-pound something on the other side. So as long as we do the same thing to both sides, we're okay. We divided the one side by V2, we have to divide the other side. And that's how we rearrange the equation. There's other ways to think of it, but this is what I'm going to go with in class. Okay, so now we've got P2 by itself, but it's a little bit messy. So I'm just going to rewrite it with P2 on the left. And I'm going to copy these down, P1, V1 over V2. You got to be real careful with all these letters and numbers to copy them correctly. So there's my equation. And now I'm going to take the numbers from the table. They're all nicely organized. Here's P1 and V1. P2 is what we're looking for, and here's V2. And we're going to plug them into the equation and solve. So P1 is 3.0 atmospheres. Write the unit. V1 is 5.0 liters. Write the unit. Divided by V2, which is 2.0 liters. Write the unit. So we've got our numbers in there. Let's look at our units and make sure they're canceling out correctly. Liters over liters cancels out, and we're left with a unit of atmospheres. And that's nice because we're calculating a pressure. And so now we use our calculator. So my calculator's not cooperating. So we've got 3.0 times 5 divided by 2. Just like the last time I did this, it's still 7.5. All of the numbers we have here have two significant figures, and so our answer should have two significant figures. So P2 equals 7.5 atmospheres. It's always a good idea to ask yourself, does that make sense? Did it change in the correct direction? So we look at the problem, and the volume was changing from 5 liters to 2 liters. It's like taking a big balloon and squishing it smaller. If we decrease the volume, then the pressure must go up. And we look at this, and the pressure went from 3 atmospheres to 7.5, so that's the right direction. What happens sometimes is that you get your 1s and 2s backwards, or you rearrange your equation wrong, and you end up going in the opposite direction. So looking for the correct direction will alert you to a mistake like that. Any questions?